So, in our modern world, we're not just constantly getting hit with information. We're often drowning in it.
Yeah, it feels like that sometimes.
Data just streams in at this incredible pace, and it's always changing. Keeping up, let alone making sense of it all, can feel like, well, like trying to drink from a fire hose while juggling.
Huh. That's a good analogy.
But for a lot of these cutting-edge applications, think real-time monitoring, personalized recommendations, complex financial risk modeling, or even autonomous systems being able to learn continuously from this constantly shifting data. Well, that's online learning, and it's not just nice to have, it's absolutely fundamental.
It's the bedrock, really.
Okay, let's maybe unpack this a bit. Today, we're doing a deep dive into a really innovative new algorithm. It's designed specifically to thrive in this chaotic data landscape.
Right.
It's called OL-MDISF, which, it's a bit of a mouthful, stands for Online Learning from Mixed Typed, Drifted, and Incomplete Streaming Features. And this is based on some pretty recent groundbreaking research published just this July 2025 by Shengda Zhuo, Di Wu, Yi He, Shukang Kwang, Xindong Wu, and others.
That's right. Fresh off the press, essentially.
So our mission today is to understand how OL-MDISF is actually built. It aims to be this unified solution, tackling three really big interconnected challenges that, traditional online learning often struggles with, or maybe only solves one piece at a time.
Yeah, they often treat them in isolation.
Exactly. So think of OL-MDISF less like a traditional model and more like a hyper-aware, adaptable organism designed for the wild, messy world of real-time data.
That's a great way to put it. And what's fascinating here is that these aren't just like theoretical problems for academic papers. They're fundamental to how real-world data actually behaves.
Right, the real headaches.
The biggest headaches, yeah.
Right.
For anyone building these systems. So the three core challenges this research dives into are, first, just the sheer messiness and variety of data you get in real-world streams, what they call mixed feature types.
Mm-hmm.
Second, there's that notorious problem where the data stream distributions themselves just shift over time, widely known as concept drift.
Always changing.
Always changing. And third, the very practical, often costly limitation, where it's simply, it's infeasible to label every single data instance you see. That leads to what they call incomplete supervision.
And they're all tangled up together, aren't they?
Completely intertwined. Solving one often doesn't really help you with the others.
Yeah, that first challenge really hits home if you've ever dealt with real-world data. It's just...
Yeah.
It's never clean, is it?
Never.
When we talk about mixed typed here, we mean data that's got all sorts of formats just living side by side. Numbers, categorical labels like customer type or product category, and often just a lot of missing values, blanks everywhere.
Yep, gaps in the data.
And it's not just statically messy either. These feature spaces can change over time. New features might suddenly appear. Maybe a new sensor comes online, or you start tracking a new user demographic.
Or a feature just becomes obsolete.
Exactly, or existing ones might just vanish. So this creates this really tough dual challenge, right? You're trying to manage the heterogeneity, the mix of types, and this temporal inconsistency at the same time.
It's like trying to map a landscape where the landmarks themselves keep changing or disappearing.
Yeah, like navigating a jungle where paths vanish and new ones appear constantly.
And that's precisely where most, traditional online learning methods tend to struggle. They often make these simplifying assumptions.
Assuming things are cleaner.
Yeah, expecting a relatively clean or consistent feature schema. Or they might focus narrowly on just one aspect, like online feature selection. They can be good at their specific niche, but they get overwhelmed pretty quickly when the entire data landscape is shifting under their feet.
So, okay, the data's chaotic. What's OL-MDISF's core strategy to even start making sense of it? This is where that copula-based latent modeling strategy comes in, right? It sounds complex. What does it actually do?
It does sound a bit technical, but the idea is actually quite elegant. Think of it like a master translator and organizer for this incredibly messy data.
Okay.
Instead of just looking at each piece of data, a number here, a category there, a missing spot in isolation, this approach builds a kind of hidden map, a latent space.
A map.
Yeah, a map that fundamentally understands how all these different data types relate to each other. It sort of uncovers the hidden grammar within your data, regardless of the type.
Ah, I see.
And that is crucial because it then allows OL-MDISF to seamlessly bring new features into this map and deal with those missing pieces without needing the old school, often cumbersome methods like, imputation to guess missing values or complex type normalization schemes.
Right, which can introduce their own problems.
Exactly. So it adapts to these highly dynamic, noisy, mixed-up data streams with remarkably few assumptions. It's almost like it speaks the native language of the chaos.
That sounds like a huge practical advantage. Makes it much more suited for the real world. But, okay, once you've got maybe a better handle on the data's inherent messiness, what happens when the meaning or the relationships within that data start to change? That brings us to the second big hurdle, concept drift.
Ah, yes, concept drift.
Define that for us and maybe why it's such a deal breaker for models that can't adapt.
So concept drift is basically when the underlying patterns or the distribution of the data itself changes over time. Sometimes it's subtle, sometimes it's really abrupt.
Like what? Give us an example.
Well, imagine a fraud detection system trained on last year's patterns. New scams emerge, maybe user behavior shifts, and suddenly its predictions are way off.
Okay.
Or think about an e-commerce recommendation engine. It might be great, but then a major holiday season hits, or a new fashion trend explodes. If the model doesn't keep up with those shifts,
its recommendations become useless.
Exactly. The critical consequence is this often abrupt, substantial drop in performance. Your once accurate model suddenly starts making really bad predictions, leading to real-world costs or missed opportunities.
We've all probably seen that, right? Your spam filter suddenly starts letting everything through after a new phishing tactic emerges.
Or your stock predictor goes haywire after some unexpected market event.
Yeah, that's concept drift hitting hard. So the really tricky part is, how do you reliably spot these changes happening in real time, especially when you don't have perfect information? Like, maybe ground truth labels are scarce or delayed.
Precisely. That's the core challenge. Now, there's been a lot of research exploring ways to adapt to drift, things like using sliding windows of recent data or ensemble techniques where you have multiple models working together.
Right.
But many of these existing solutions tend to focus on just one aspect of drift. Or, crucially, they often rely on having labels readily available to even detect that a change has happened.
Which you often don't have immediately.
Exactly. And this is where OL-MDISF brings something really new to the table. It incorporates this quite sophisticated temporal drift detector that's based on two complementary signals.
Okay, two signals. What are they?
So the first one is what they call ensemble entropy. You can think of it as the model's internal self-check.
Like listening to itself?
Kind of, yeah. It measures the level of disagreement among its internal component models. If these components suddenly start disagreeing significantly about predictions, it's a strong hint that the underlying data patterns they were trained on are shifting.
Interesting. And the second signal?
The second is called latent mismatch. This actively tracks how the structure is changing within that learned copula-based representation, that hidden map we talked about earlier.
Ah, checking the map itself.
Exactly. If the overall structure or geometry of the data in that latent map starts to look fundamentally different from what it expected, it flags a likely drift.
And the key is doing this without labels.
That's the beauty of it. This dual mechanism enables pretty robust real-time detection of concept drift without needing those ground truth labels. This allows for remarkably smooth model transitions even when the data streams are behaving really erratically. It achieves strong adaptability over time while also cleverly avoiding catastrophic forgetting, basically. It doesn't just throw out all the old knowledge when adapting to the new.
That's incredibly powerful, detecting fundamental shifts without needing someone to explicitly tell you they've happened. Okay, that brings us to our third and maybe the most pragmatically difficult challenge: incomplete or noisy labels. In so many real-time or streaming situations, getting perfectly labeled data is just, well, it's often incredibly hard or expensive or slow. Why is that?
Yeah, it's a huge practical barrier. Labeled data is frequently sparse or delayed or just plain noisy because of a whole host of real-world constraints.
Like cost.
Cost is a big one. Imagine an IoT sensor network monitoring industrial equipment, getting human experts to label every single detected anomaly.
Yeah.
Hugely expensive and time-consuming.
Right.
Or, in medical diagnostics, lab results take time, meaning the labels confirming a condition might arrive much later than the initial sensor readings or imaging data. Latency is another factor.
And privacy.
Privacy, absolutely. In sensitive areas, getting detailed ground truth labels might simply be impossible due to data protection rules or user consent issues.
So traditional supervised learners, they just fall apart here, don't they?
They really struggle. They're built on the assumption of a steady, reliable flow of accurate labels to learn and maintain performance. When that flow is patchy or unreliable, they degrade quickly.
People have tried to fix this, though, right? With things like active learning.
Oh, yeah. There are definitely approaches. Online active learning, where the model tries to be smart and only asks for labels for the most uncertain or informative instances, is one. And semi-supervised schemes try to use a small label set to kind of propagate labels to the unlabeled data. They've made progress, but they still have limitations, especially in these really dynamic scenarios where you've got the mixed types and the drift and the missing labels all happening at once.
Okay, so if you can't count on having consistent, perfect labels, how does OL-MDISF manage to learn effectively? This seems like another area where it takes a really unique path.
It really does. Remember that copula-induced latent space we discussed? That hidden map where the sort of geometric relationships between data points are preserved, even across all those different input types.
Yeah, the map idea.
OL-MDISF operates directly within that space. And what this means intuitively is that it can intelligently propagate pseudo-labels based on local geometric proximity.
Okay, break that down. Pseudo-labels, proximity.
Right. So imagine your data points plotted in this hidden map. If you have a few points that are labeled, say, fraud, the algorithm looks at their nearest neighbors in that map. If those neighbors are structurally very similar in this latent space,
it assumes they're likely also fraud.
Exactly. It confidently assigns a pseudo-label, a temporary inferred label based on that close geometric similarity. It's like filling in a complex coloring book by looking at the lines and the colors you do have, even if not every section has a number.
And it does this without asking for help.
That's the key. This structure-aware propagation is inherently tolerant of uncertainty. And crucially, it doesn't rely on external mechanisms to query for more labels. It's more self-sufficient.
Wow.
And sort of tying things together, that latent drift detector we talked about, it actually supports these label-aware updates even when ground truth is missing. This provides robustness not just to the missing labels, but also to potential noise in the labels you do have, especially as the environment evolves.
Okay, so let me try and wrap my head around this. What this all means when you put it together is OL-MDIS isn't just like 3 separate fixes bolted together. It sounds more like a single, elegant framework that understands how these problems, the mixed types, the drift, the missing labels, are fundamentally connected.
Precisely. And that's arguably the most revolutionary part. You're moving away from trying to juggle 3 separate, constantly shifting puzzles simultaneously.
Yeah.
Instead, you get one intelligent system that kind of sees the whole chaotic picture of real-world data and adapts holistically, seamlessly. It's less patchwork, more integrated intelligence for continuous learning.
That makes sense.
And this specific document we're drawing from, it actually serves as a really comprehensive extension to their original paper from TKDD 2025. It provides this massive set of experiments. They tested it across 14 different real-world data sets.
14? Wow.
Yeah, and under 2 distinct types of drift scenarios. One they call capricious, where changes are really abrupt and unpredictable.
The nasty kind.
The nasty kind, yeah. And trapezoidal, where the changes are a bit more gradual. So the paper is really designed to be a solid, reproducible benchmark and a vital technical resource for researchers who are wrestling with these messy, real-world data stream problems.
And the results they present, the experimental insights, they sound really compelling in backing up this holistic approach.
They really are.
They show these cumulative error rate, or CER trends, across all those 14 data sets. And apparently, these clearly demonstrate OL-MDISF's efficiency and effectiveness compared to a whole bunch of other well-known online learning algorithms.
That's right. They compare it against methods like OS-LMF, OVFM, Phobos, OMR, OL-VDS, OL-CDS, and ORFL, quite a lineup. And OL-MDISF consistently shows better performance across these diverse, challenging, real-world data sets.
It's not just about the overall score, though, is it? They did deeper dives.
Exactly. Beyond just the headline performance, they conducted crucial ablation studies. This is where you, surgically remove parts of the model to see how much each specific component actually contributes to the final result.
Ah, to see if everything's pulling its weight.
Precisely. They tested variants like OL-MDISFF and OL-MDISSF, whether it's the way it handles mixed-type features or its specific label propagation mechanism, significantly adds to its overall impressive performance. No redundant parts.
And maybe the most striking part for practical use. They ran these sensitivity analyses, right? Testing how it copes when labels go missing.
Yes. This is really telling. They tested its performance with 10%, 50%, 70%, and even a staggering 90% of the labels completely missing.
90%? That's barely any supervision.
Almost none.
Yeah.
And this is where OL-MDIS truly sets itself apart. The results showed it maintained significant robustness even with these extremely high levels of missing data. It really validates its strength in these weakly supervised scenarios.
And how did it compare to simpler methods in that test?
It blew them away, essentially, especially when compared against various standard-based classifiers, things like logistic regression, LR, PAKE, perceptron per ridge, SGDC, which would normally just completely fall apart under such severe label scarcity.
Okay, so putting it all together, in a nutshell, OL-MDISF really seems to offer this powerful, genuinely holistic solution to some of the absolute toughest, most interconnected challenges we face in online learning today. It feels like it's moving the field forward quite a bit by tackling these problems not as separate issues, but as facets of a single, complex, dynamic system.
I agree. It truly reemphasizes the importance of designing a single, unified model that can robustly handle the inherently messy, constantly changing, and often incomplete nature of real-world data streams.
Yeah.
You don't want separate, potentially conflicting solutions trying to fix each problem in isolation. This integrated approach is where the real power lies for practical deployment, I think.
Yeah, it really seems like it. So, thinking about this, what stands out to you listening to this? Consider the data streams maybe you encounter in your own life or work. Maybe it's from smart home devices or health tracking apps or even just navigating your social media feed. How might a system like OL-MDISF, something truly capable of handling mixed-typed, drifting, and incompletely labeled data all at once, how might that revolutionize future applications? Think about optimizing smart cities, enabling truly personalized healthcare, or building much more adaptive, resilient financial systems. The possibilities, quite frankly, seem really exciting.